Our first section is going to deal with functions. Now this is going to be, partly review for a lot of you, but we are going to go into more depth than you probably did in your, intermediate algebra course or equivalent. It's really important in mathematics to understand what a function is. At this level and beyond, every course that you're going to take is going to deal with functions. So it's, a central concept in mathematics. And even in your science classes, they're going to use functions. Your business classes will use functions as well. Now, I do expect that you would have read these, through these notes before we start here. So I'm not going to sit and read all of this to you. Therefore, if you haven't read it, you should pause the video and read through it. I'm going to refer to everything as, if you have read it. So that's the nice thing about video. You can just, if you haven't done it yet, pause it, go ahead and read it, and then, start the video up. So let's get started here. So when you're talking about functions, it's good to have a notion of the more general concept of a relation, what that means. And so a relation is just, you basically have two sets, and there's some pairing up of the elements in the two sets. The relationship of how these are paired up doesn't really matter, but the idea there's a relationship, and that's why we call it a relation. So the first set is called the domain, and the second set is called the range. We usually use the variables x and y, and you should have experience using those variables quite a bit in mathematics. But of course you can use other variables as well. But x is usually the domain variable, and y represents the elements in the range. Okay, so here I've got some examples here, just some relationships between two sets. You can read through those. Okay, well, let's look here. We have some other examples, and I talk about different ways to represent relations. And there's 4 basic ways. Now in mathematics, we usually use numbers, but in some of these examples I have, names, and that's okay. But when we really get down into our work, we'll, of course, be using numbers. So here we call these mappings, where you just have, kind of a picture of some sort representing everything in the first set, which is the domain, and then the second set, which is the range. Here the domain is made up of a list of names, the range is a list of ages. And you can see one person can only be one age at a time, and so there's just a one-to-one pairing up of the names and ages. Now those same people also are taking some courses, and they can of course take more than one course, so some of these names go to more than one course. Both of these are relations. The second way would be just to list the ordered pairs defined. So you have this mapping, you could just rewrite it in terms of ordered pairs. And we've got the set brackets here to show this is a set of ordered pairs. So this first example is just this same relation, just in ordered pair form. The second one, I didn't list every possibility here because it was getting long, but the ellipses, you could list every possible pairing that I have, the lines where I have lines drawn here. And then the third example is just some numbers that I put in there. So those are all relations. Another way we can represent a relation is I was just checking my screen here, making sure I have my paper in the frame. Show the relationship between x and y with a formula, and so then we have an equation. And so here's 3 examples of that. And then we can use graphs. And so the graph, well, let me go back to equations. So you don't have an explicit list of ordered pairs here, but of course you could plug in a value for x, say x is 0, and then you could solve for y and get an output for y. Y would be 1, and so there is an ordered pair that corresponds, that this equation gives us 0, 1. And you could come up with an infinite number of ordered pairs defined by this equation. Then, and we can do the same thing for all of these. And then with graphs, you can see like this relationship here has an ordered pair 3, 7, 0, 2, -4, 5, and -4, -2. So we've got the pairing up between the two sets. The x's are, the domain values, the y is the range, and you can come up with a, if I wanted to do a map, I would just say, 3 is mapped to 7, -4 is mapped to 5 and -2, etc. Right? You can do, there's 5 ordered pairs. I only did 3. All right, and then this one, you can see there's exactly 5 ordered pairs. Here we have an infinite number of ordered pairs defined by this relation. Not only do you have things like 0, 3, 1, 3, 2, 3, but everything in between, 0.5, 3, 0.63, etc. These arrows are showing this keeps going. So lots of ordered pairs we could come up with given this graph. Excuse me, my voice is a little froggy. Okay, so then this brings us to the idea of a function. Functions are relations, but there's something unique about them that needs to happen. And that is when you put in the input, you cannot get out more than one output for that one input. So like in this previous example with this graph here, because for x's are inputs, -4 actually, when you plug that in for your input, goes to 2 different y coordinates. It goes to 5 and it goes to -2. So this one is not a function. There's a relationship here. It's a relation, but it's not a function. Okay, so here I give some more examples. These 3 examples are all functions. So, like, if you went shopping and you bought 2 items and they're the same exact item, you would expect the price to be the same when those 2 items are scanned, right? And if they weren't, you would be angry. So it's important that we have this consistency with the function. So the input would be the item, the output is the price. That should be the same every time on a given day. The next day it might go on sale, but that's different. It's a different point in time. To each automobile, there corresponds a license number. It would be confusing if they had more than one license number, right? To each number, there corresponds its square. So, when you square 5, you get 25 every time. Now, the thing that gets a little confusing is people think, well, -5 squared is also 25. That's okay, because every time you square 5, you get 25. Every time you square -5, you get 25. It's okay if 2 different inputs have the same output. What's not okay would be if 5 squared was 25 one time and then 5 squared was 30 the next time. That wouldn't make sense. So this is also a function. All right, so here's a more formal definition. A function is a rule that takes each element in one set called the domain and assigns it to exactly one element in a second set called the range. So the rule in this example is square the number. In mathematics, we can use formulas to represent our rules. Okay. So you can, even though we have these 4 different ways to represent functions and relations, keep in mind they all are sets of ordered pairs. It's just different ways to represent set of ordered pairs and how are those things paired up. For functions, you've got one, you've always got the input-output idea. The input x, if you have a formula, apply the formula to it, you get your output y, and that y depends on your input, and so that's why we call the input the independent variable and the output the dependent variable. Okay, you can go ahead and read through this, but I've talked about this already. Functions are relations, but there's something specific that we need to have happen in order for the relation to be considered a function. So not all relations are functions, but all functions are relations, of course. Excuse me. And since a function is a relation, we can use those 4 ways to represent it. Okay, so in mathematics, of course, we often use the formula idea. And if you do have a function, you should be able to isolate y and write a formula in terms of x. This is your rule here then, and this, this tells you what to do to your input. X is your input, you should square it, and then when you get that result, take away 2 times the input, and then get that result, and then add 1 to that. That's going to be your output. Now, again, we usually use x and y, but we don't have to. So you should get used to the, kind of phrasing, something is a function of something. That means the is your equal. So w is a function of t would mean we have w equals some formula in terms of t, and there should be no other variable there. If w is a function of t, that should be the only thing, or the only variable in your formula. If there's 2 variables, it's okay to have 2 variables, but then it's a function of 2 things, not just one. For example, like, in the area is length times width formula for a rectangle, the area of a rectangle is a function of both its length and its width. All those formulas from geometry, that, well, I don't know if you know them all. You may not have them all memorized, but you're familiar with them. Those are functions of, whatever length, or we'll just say length. So area is a function of length and width. Width is a length as well, right? Okay. So if we understand the relationship between 2 sets, we can actually go ahead and write the formula ourselves. So here's a real simple example. It says Joe makes $12 an hour. Write a function for the amount of money he makes in 1 week, which we're going to call S, and that represents his weekly salary, if he works for X hours a week. So we want a function for S. So that means we're going to have S equals, and how can we calculate S, his salary? Well, he makes $12 an hour. He works for X hours, so that's going to be 12 times X. Most of us have worked hourly jobs, and we know how to calculate pretty easily how much we'd make, right? So there's our formula. This is S is a function of X. And then in example 2 is related to this. It says, what is the independent variable and what is the dependent variable? Well, the independent variable is X, the amount of hours he works. That's our input, and then his salary depends on how much he works, so the dependent is S. All right, next question. If he's not allowed to work for more than 40 hours a week, what are the domain and range? Okay, so this, sometimes when we have an application, that affects our domain and range. If this were just a formula and we had no other information, X could be any number, because you can take any number times 12 and get a result. But in this case, he's constrained by how much he can work. So X, for the domain, has to be more than 0 or possibly equal to 0, because he might not work at all, right? And then the greatest it can be is 40, and he could work 40, so again, use equality there. If he can't work 40, then you would make that a strict inequality. So X is between 0 and 40 inclusive, and of course the label here is hours. Or in interval notation, if you don't know interval notation, you should go back and learn that. I'm not sure which section of the book it's in off the top of my head, but you can look in the index and find it. And then the range here, so the domain is the set of inputs, that's how many hours he works. You can maybe hear my dog barking in the background, sorry. The range is his salary. So you just go and you say, okay, well, he's got this continuous amount of hours he could work in a week. If he works no hours at all, he's not going to make any money. The range is the amount he's making, right? And then this is going to be S instead of X, his salary. And then the most he can make is if he works the 40 hours. So if he he's working 12 hours or 40 hours for $12 an hour, that's 480. So 480, this is dollars in this case. You could put dollar signs here if you want, but we usually don't for domain and range. And then, the interval notation would be 0 to 480. Okay. The next example just has some ordered pairs. So we're going to determine if these are functions. The domain and range for a list of ordered pairs is really easy. The domain is just, the set of inputs or x coordinates. So 3, 2, -1, and 0. I like to reorder, and or I should say put them in order. And then the range are the y's, 4, 5, 4, and 0. 4 is in there twice. You don't need to write it down twice. So it would be 0, 4, 5. And then you want to ask yourself, well, is this relationship a function? So when you plug in 3, you get out 4. You plug in 2, you get out 5. You plug in -1, you get out 4. You plug in 0, you get out 0. And it might help you to use the mapping to visualize this. Notice these two are going to the same output. 0 goes to 0. None of these are going to more than one place. And so yes, this is a function. Okay, and I said if it's not a function, explain, but you should be able to explain if it is a function as well. So this is a function since each input goes to exactly one output. Okay. Now it's okay. It's sometimes not in the, we wouldn't list it as an ordered pair in this case, but you could have an input that doesn't go to an output if you're plugging in something that's not in the domain. But that comes into play more in the formula idea, so we'll hold off on that. All right, here now you've got -2 going to 2. Well, here, let me list domain and range first. Sorry, that's the easy part. So -2 and 1 is the domain. The range, 2, 5, 6. And then you've got -2 going to 2, 1 going to 5. But now you have -2 also going to 6. Since you've already listed -2, we're not going to put it here and put 6. We're going to say, oh, wait a minute, this goes also to 6. So this is not a function since -2, you could say maps to or is paired with, however you want to word it, or just goes to two outputs. Two distinct outputs. So the thing you want to watch for here when you have a list is, are any of these first ones the same? It won't matter if the second ones are the same. Check the first ones, and if those are the same, then the y's better be the same. In other words, you've listed the ordered pair twice, then it would still be a function, but we generally don't list the same ordered pair twice, so you want to check if these are different, then you don't have a function. All right. Now, if we have formulas, we want to also be able to tell if those are functions or not. And so it's really easy if y is already isolated and you've got the formula in terms of x on the other side. Like in A, in this example, we're going to determine if these relations define y as a function of x. This is so simple because you've got y in terms of x, yes. Y is written as one rule in terms of x, or one formula, however you want to state that. So it is a function. Again, we're using x and y here, but if this said w and t, we would have w here and t here. Okay, but of course y is not always isolated, so then what we'll do is isolate, or try to isolate y. Sorry, that's messy. Let me rewrite that. Try to isolate y if needed. Okay, now let's do b. Now b might look like y is isolated appropriately, and you've got your rule. But because of the plus or minus here, we actually have two distinct rules. We use this as shorthand to represent this. So y is x or y is negative x. So if we plugged in, for example, if we let x equal 4, then y is 4 or y is negative 4. Since 4 is going to two different values, this fails to be a function. No, y is not a function of x. You've got many, cases where you would plug in an x and get out two different y's. All right, C and D, let me get this organized. C and D I kind of want to do together because these are they look very similar to people, but they're two different results here. You want to try to isolate y in both cases. In the first one, when you isolate y, you've got absolute value of y as 4 minus 2x. Remember this absolute value here, given, now you would need this side to be positive in order to get an equation that you can solve, right? Or 0. You can't, it wouldn't make sense to say absolute value of y is negative 4, that would have no solution. That's what I'm talking about. And that comes into play with the domain. There's only certain numbers you can plug in for x that will give you an equation here that has a solution. But more about that later. My point is if this results in a positive number, there's actually two numbers here that would work. For example, if absolute value of y is 5, that would mean that y could be 5 or y could be negative 5. Both of those things would make this equation true. So remember that absolute value, we have two cases. Now this is when we've isolated the absolute value and we want to know what things make this true. Now, this of course isn't a 5 over here, it's a formula, but the same idea holds. This is going to be true if y is equal to this number or y is equal to its opposite. And because it's a formula, you want to make sure you take the opposite of the whole thing. So we have two formulas for y in terms of x. So it's not a function. But in D, when you isolate y, so notice y doesn't have absolute value this time. You just get 4 minus 2 absolute value of x. That is one formula for y in terms of x. So this is a function. It doesn't matter that you would get, if x is 4 or x is negative 4, you're going to get the same y out. That's okay because x is just two different pairings. We're not solving for x here, so that's why we don't get the two results. So let's say if for example, if x is 0, y is 4. If x is 3, see that's 6, 4 minus 6 is negative 2. And if x is negative 3, we're still going to get out negative 2, but again, that's okay. 3 only goes to negative 2. It doesn't go to a different number. Negative 3 only goes to negative 2. This is by no means a proof, but it helps to sometimes plug some numbers in and see what's going on. So this one is a function. Okay, now in E, this one should be really straightforward. In fact, you should recognize this if from your previous course as a line, right? This is a linear equation. And so we can easily isolate y. When we're doing that, we're actually putting it in slope-intercept form. Negative 4y is negative 2x plus 5. Divide everything by negative 4. Y is negative 2 over negative 4 is a half x. And then 5 over negative 4 is negative 5/4. So yes, one formula for y in terms of x. By yes, I mean it's a function. Okay. Now that brings us to function notation. You should have some experience with using function notation. When we use function notation, we have y isolated in terms of x, and that y, instead of using y, we replace it with a notation like f parentheses x, which is read f at x or f of x. Now, we didn't use function notation, of course, in our salary example, but if we did, we would write s at x is 12x. S is a function of x. So the f is, not, excuse me, you don't have to use f, but we use it a lot because function starts with f. But here we have different letters. The nice thing about this is now if we can use different letters, it's easy, I can say function g and I'm talking about this formula, right? This side here represents the y coordinate, and this in here is your input. So in all of these, it's telling you whatever you plug in here, this is where you're going to put it on the other side, inside of the formula. The x is like a placeholder, really. It's telling you what to do to what you're plugging in. Okay. So there's some advantages. I already mentioned the first one. We can give things different names now. It makes it less confusing. The other really nice thing is this notation. Instead of writing y equals, if I just write y equals 3, I don't know anything about x. But when I write f at 2 equals 3, I know that y is 3, but I also know my input, which is x. X is 2. And so I wrote that here. So it's really nice. Okay, here I have an example. F at x is 5x squared minus x. We want to find f at 2. So that's just saying, well, plug 2 into my formula. You've all replaced variables with constants before, so this shouldn't be difficult. So 5 times 2 squared minus 2 is what we're plugging in for x here. So 2 squared is 4. 4 times 5 is 20. 20 minus 2 is 18. So we would write f at 2 is 18, not f at x is 18. A lot of students will put this as your final answer. If you do that, I'm going to mark it wrong. F at x is not 18. F at x is right here, 5x squared minus x. This would imply that no matter what you plug in for x, the output is always 18, which isn't true. The output is 18 when the input is 2. So this is what you want to write down. F at 2 equals 18. Don't write that. That shows you don't understand what's going on. Excuse me. F at negative 3, we have 5 times negative 3 squared minus negative 3. Negative 3 squared is 9. Excuse me, I'm going to have to sneeze. And then negative 3 is plus 3. So we've got 45 plus 3, which is 48. All right, the next one has a fraction in it, which of course makes a lot of people nervous, but don't be nervous. When you deal with the fractions, I do want you to leave them as fractions, no decimals, unless we're doing an application that involves decimals, or the problem, you know, if this started out with decimals in it, then work with decimals. But we're going to leave it as a fraction. So negative 1/5 squared, and then minus x becomes minus negative 1/5, right? So these were your x's, and that's where they were. Okay, negative 1/5 squared is 1/25, and then plus 1/5. Well, 5 times 1/25 is 1/25, or 1/5, I'm sorry. 5/25, which reduces to 1/5. Plus 1/5 is 2/5. Okay, so f at negative 1/5 is 2/5. All right, in D, f at a, now a is not a constant, it's a variable, but that's okay. We'll plug it in where x was, so this will be 5a squared minus a. That's actually the easiest problem on the page. That's it. It's basically still, you know, our function, just with a different placeholder in it, with a in it instead of x. All right, let's do one more, and then I think I need to pause the video, take a little break. We got a lot left. This is a long one. Okay, so here, it's the same function we used before, and then we have another function g. So in part A, since this says g, we know that we're going to use this formula. So we've got 2 times negative 1/2 cubed minus negative 1/2 plus 1. So 2 times negative 1/8, you take negative 1/2 times itself 3 times, you'll get a negative 1/8 plus 1/2 plus 1. 2 times negative 1/8 is negative 2/8, and negative 2/8 reduces to negative 1/4. All right, so here's where I was talking about. Don't plug this in your calculator and use decimals. Get a common denominator. If you know this starts with a fraction, answer with a fraction. 1/2 is the same as 2/4. 1 is the same as 4/4. So we've got 6/4 minus 1/4, which is 5/4. B. Now we're back to the first function, f at x, 5x squared minus x. And this is saying find f at x plus h. This gets confusing because there's an x here and there's an x here. What you have to remember when we do a problem like this is that these x's are not the same. So this represents a number. Doesn't matter what was up here. Just think of this as a blank spot. And instead of the x, you're plugging in the x plus h in its place. So in your formula, you know, which was f at x, think of that as a blank. And now you've got this blank here. Blank, right? That's not a subtraction, that's supposed to be a blank. The x plus h is going to replace the blanks. So it's 5 times x plus h squared minus x plus h. So don't think of that, you know, x as a variable. Think of it as a placeholder. I mean, it is a variable, of course, but like that's a blank spot that you can plug things into. What I don't want you to do is say that f at x plus h is f at x plus f at h. Okay, that's wrong. You're plugging the x plus h into the blank spots. All right, once you get this part, the rest is just algebra. You're going to square this. Don't forget when you're squaring a binomial, I'll do it over in the margin here. This is not x squared plus h squared. You do have x plus h times x plus h, so you're going to have, you do get x squared, but then you've got your inside and outside products. So you get x squared plus xh plus xh plus h squared. These add up to 2xh. So don't forget the middle term, which comes from your outside inside products, which will be the same, so you're going to have two of them. You know, and like anytime you square a binomial, you should have a middle term. All right, and then distribute the sign here, minus x minus h. Now we're almost done. 5x squared plus 10xh plus 5h squared minus x minus h. Because there's no like terms, that's it. That's our final answer. Okay, well, let's take a little pause here. I need to get some water.